how a series circuit works in comparison to a parallel circuit was one of the things I found most difficult to understand when I was starting off in training in electrical installation works. Had to learn the theory, had to learn the science. So I'm going to have a little look at what's going on in these two different examples of circuits. So at the top here we have a series circuit, so what shows one wire with the two resistors connected one after the other along that wire. The bottom circuit has a wire that branches into two pieces, so we now have two wires with one resistor connected on each, and then those two branches join back together. So that's the basic fundamental principle of our series circuit and our parallel circuit. And if you're studying electrical installation, you'd have been told that on a series circuit the total resistance is equal to the sum of the resistances in the circuit. So our formula RT equals R1 plus R2, with this being R1 and this being R2, tells us the circuit resistance. So there we have R1 and there we have R2. On a parallel circuit, it's much more difficult. You might have been told something like, I don't know, that the reciprocal of the total resistance is equal to the sum of the reciprocals of the individual resistances. It's not very easy, and actually the formula that goes with it is not particularly helpful either, because it doesn't give you RT, it gives you 1 over RT, which is what a reciprocal is. It's 1 divided by a value. So 1 over RT equals 1 over R1 plus 1 over R2, and that's not an easy formula to use, and doesn't make understanding the circuit particularly easy either. So we need to drill down into this a little bit more, but before we do that we need to remember the biggie. Okay, the most fundamental thing that helps us understand these circuits. V equals IR. Okay, Ohm's law, that's critical. You've got to be able to use Ohm's law to analyse the circuit, to work out what's going on. So let us have a look at a series circuit, just to remind ourselves what's happening in our series circuit and how it works, what's going on. So we've got our two resistances, R1, oh dear, look at that, I'm on the fat one, don't want that, R1 and R2. Now formula was RT equals R1 plus R2, and let's give these some values. So let's say that R1 is 10 ohms and R2 is 5 ohms. So our formula RT equals 10 plus 5, which means RT equals 15 ohms. Okay, nice and straightforward. We can then look at how Ohm's law works in this circuit. Let's assume we have got plus 10 volts at this end and 0 volts at the other, so that gives us a total voltage drop across the circuit of 10 volts. It's really important to remember. Now that 10 volts needs to be dropped across the load resistors. We can assume that they are one resistor, RT, so we can say that V is equal to IR, and in this circuit we would then be able to determine the current, so we could say that I is equal to V over R, and then put some numbers in there. I is equal to 10 volts over 15 ohms, which means that I is equal to 0.67 rounding amperes. I is equal to 10 over 15, which gives us 0.67 amperes. Okay, so that's our series circuit solved, more or less. There's a couple of little bits in there. We also need to look at the how the voltage is dropped across this circuit. Okay, so we will have proportionately, we've got 2/3 of the voltage dropped across our 10 ohm resistor and 1/3 dropped across here. So we've got a voltage across this resistor, VR1, and we've got a voltage dropped across this resistor VR2. So VR1 is equal to, remember V equals IR, 0.67 times 10, VR1 equals 6.67 volts. I'm remembering I'm rounding here, trying to keep it as accurate as I can. VR2 is equal to our current 0.67 times 5, because we've got a 5 ohm resistor there. Okay, so VR2 is going to be equal to, well, it's going to be 3.33 volts. Okay, we have 3.33 to 6.67. You're going to end up with your nice value of 10 volts, our total voltage drop on the circuit. So there's our series circuit, reasonably simple to deal with. Now, parallel circuit, this is where things do get a bit more tricky. But Ohm's law will be our friend in this. So let's put some values into this circuit. We'll use the same values actually. So we'll take our R1 and our R2. And we'll say that R1 is 10 ohms, R2 is 5 ohms. Let's say that we apply 10 volts across the circuit. So we've got plus 10 volts at this end, we've got 0 volts at that end, and so we are dropping 10 volts across that circuit. So that's fundamental. We must drop that 10 volts. Now what happens within this circuit? Well, we can ignore one branch. We can just deal with another branch. Okay, we deal with each branch individually. So this branch here has got 10 volts dropped across it. Okay, the top branch. Also, the bottom branch has got 10 volts dropped across it. So we can work out the current through each branch really simply, just using Ohm's law. Remember, Ohm's law says that V equals I times R, and we can turn that into I equals V over R. That's just the transposition of the formula. So let's come in here and let's take that top branch, and we can say that I, R1, that's the current passing through R1 through the top branch of the circuit, is equal to V, okay, and I'm going to say VR1. The voltage dropped across resistor 1, it's the supply voltage, but it's good to keep these things precise. VR1 divided by R1. Let's put some figures in that. Current R1 is equal to 10 volts divided by 10 ohms. IR1 equals 1 ampere. Whew, that was easy. So R2, IR2 equals VR2 over R2. So in this case, the current passing through this resistor, IR2, is equal to the voltage dropped across it, our 10 volts, divided by its resistance, 5 ohms. So we end up with 2 amperes there. That makes sense. Lower resistance, higher current. Higher resistance, lower current. So how much current do we actually have in the circuit? Well, there's a law, Kirchhoff's law, one of Kirchhoff's law, states that the current entering or leaving a node on a circuit will be equal to that coming in. So whatever comes in must come out. So if we have current coming out of this point here, so some goes through this side, okay, from the supply. We also have some coming from this side through the other resistor. So we've got 2 lots of current flowing in the circuit. Well, we can say that IS, current supply, the circuit current, the total current if you like, is equal to IR1, current passing through this side, plus IR2, the current passing through the other side. Okay, let's put some figures in there, which is equal to 1 ampere from the top branch plus 2 amperes from the bottom branch, which equals 3 amperes. So we've actually solved that bit of the circuit quite easily. That wasn't that tricky at all. But there's one thing left to do. We don't know what the total circuit resistance effectively is. So let's have a look. So RT, and this is in a parallel circuit. Why are we using that weird formula? Well, let's use the same circuit. So let's remember we had R1 was 10 ohms, R2 was 5 ohms, VS, our supply voltage, was 10 volts. Oops, I forgot my ohm symbols. And our IS was 3 amps. Yes, 3 amps. Okay, so our RT, using Ohm's law, so let's just remind ourselves, V equals IR, which turns into I equals V over R, and also R equals V over I. We're going to use the bottom one here. RT is equal to VS over IS. So the total resistance is equal to the supply voltage divided by the supply current. So let's put the figures in. RT is equal to 10 volts divided by 3 amps. So RT equals 3.3 recurring ohms. How do you get to 3.3 recurring from 10 and 5? Well, that's the tricky bit. To do this, we need to go back to the formulas which gave us our current. Okay, so we've got a couple of formulas that describe the current of the circuit. So first of all, we have IS itself, which is equal to VS over RT. We have got IR1, the current through the top branch of the circuit, which is equal to VS again over R1. And we've got IR2, the current through the bottom branch, which is equal to VS over R2. We then need to take this little piece of information here and bring that into our next section, where we say IS is equal to IR1 plus IR2. Current through the top, through this whole circuit is equal to the top branch plus the bottom branch. And we know that these values are the same. Now note this VS is the same in each one, it's just the bottoms that change. So we can say that therefore VS over RT is equal to VS over R1 plus VS over R2, and as I just said, VS is common to all of these, so it doesn't matter what VS is. It could be 100, it could be 1,000, it could be 2, it could be 30 milli, whatever, but we'll change it to 1. 1 over RT equals 1 over R1 plus 1 over R2. That is the bit that makes sense. And to find out what RT is, once you've completed this part of the formula, you need to flip your fraction upside down. So we're just going to have one more crack at this just to finally get that there. So 1 over RT is equal to 1 over R1 plus 1 over R2. 1 over RT equals 1 over 10 plus 1 over 5. You can't add tenths to fifths, so we go 1 over RT is equal to 1 tenth plus 2 tenths equals 3 tenths. So 1 over RT equals 3 tenths, which means that RT, flip the fraction, is equal to 10 over 3. RT equals 3.33 ohms. There you have it.